Right now, a thin bubble of magnetized wind is the only thing standing between you and the most hostile environment in the known universe. Beyond our sun's protective reach lies a realm so empty that a single hydrogen atom drifts through every cubic centimetre with no companion beside it. Temperatures swing from near absolute zero to millions of degrees within the same cubic light year. Radiation that would shred your DNA pours in from every direction without anything to stop it. 2 human-made spacecraft have crossed into this abyss, and what they found rewrote everything we thought we knew about the space between stars. This is not the gentle darkness of science fiction. This is interstellar space, and its true nature is far more terrifying than silence. If you enjoy journeys that change how you see reality, consider tapping that like button and subscribe. Now, settle in, get comfortable, let's begin. The sun is doing something right now that most people never consider. It is screaming into the void, not with sound, because sound cannot propagate through vacuum, but with matter. Every single second, our star ejects roughly 1 million tons of charged particles outward in every direction at speeds exceeding 1 million miles per hour. Protons, electrons, and helium nuclei stream away from the solar surface in a torrent so violent that it strips paint-thick layers of atmosphere from any unshielded body in its path. This relentless outpouring of material is called the solar wind, and it has been blowing continuously for roughly 4.5 billion years, ever since our star ignited and began fusing hydrogen in its core. But the solar wind does not simply scatter into infinity and vanish. It does something far more important. It inflates a structure, a vast, dynamic, invisible bubble of magnetized plasma that surrounds our entire solar system and pushes outward against the pressure of the galaxy itself. Scientists call this structure the heliosphere. Most people have never heard the word, yet it may be the single most consequential boundary in their lives, the difference between an environment that supports life and one that would slowly destroy it. The heliosphere is the sun's domain. Everything inside it is shaped, governed, and protected by our star's magnetic field and particle output. The magnetic field lines that originate at the solar surface are carried outward by the solar wind, twisting into an enormous spiral pattern that astronomers call the Parker spiral, named after the physicist Eugene Parker, who first predicted the solar wind's existence in 1958. At the time, Parker's proposal was controversial. Many physicists dismissed the idea that the sun could continuously emit a stream of charged particles fast enough to reach the outer solar system. He submitted his paper to the Astrophysical Journal, where both reviewers recommended rejection. The editor overruled them and published it anyway. Within a few years, direct spacecraft measurements confirmed that Parker was right. The solar wind was real, and it was everywhere. Those magnetic field lines, carried outward by the wind, wrap around the sun's equatorial plane and extend outward for billions of miles, creating a magnetic architecture that defines the local space environment. Inside this architecture, conditions are fundamentally different from what lies beyond. The particle population is dominated by solar material. Protons and electrons from the sun vastly outnumber particles originating elsewhere. The magnetic field traces back to a single source, our star, giving the entire region a coherent magnetic identity. And critically, the heliosphere acts as a shield against one of the most persistent threats in the galaxy: galactic cosmic rays. High-energy particles, primarily protons but also heavier nuclei, that have been accelerated to extraordinary speeds by supernova shockwaves and other violent processes scattered throughout the Milky Way. They stream through the galaxy in every direction, carrying energies that can shatter atomic nuclei and damage molecular bonds in biological tissue. Without the heliosphere, they would bombard the inner solar system with significantly greater intensity than what we experience on Earth. Estimates from NASA and the European Space Agency suggest that the heliosphere reduces the galactic cosmic ray flux reaching the inner solar system by roughly 30 to 50% during periods of elevated solar activity, and by a smaller but still meaningful margin during solar minimum. This shielding is not perfect. The highest energy cosmic rays punch through regardless, but the reduction is significant enough that removing it entirely would measurably alter the radiation environment on Earth's surface, with potential consequences for atmospheric chemistry, mutation rates, and biological exposure over geological timescales. Every human civilization that has ever existed flourished inside this bubble. Every spacecraft ever launched remained within it, with exactly 2 exceptions. Every planet, moon, asteroid and comet we have ever studied, with close-range instruments orbits inside the heliosphere's protective embrace. The bubble is our cosmic shelter, inflated and maintained by the tireless nuclear furnace at the center of our planetary system. But all shelters have walls, and all walls have an outside. The heliosphere does not end abruptly. It transitions through a series of distinct layers, each marking a different phase in the interaction between the outward-pushing solar wind and the inward-pressing interstellar medium. Understanding these layers is essential to grasping where interstellar space truly begins and why crossing that threshold changes everything. The outermost region, still clearly dominated by fast-moving solar wind, extends from the Sun outward to a boundary called the termination shock. Throughout this vast inner zone, the solar wind races outward at supersonic speeds, typically between 300 and 800 kilometers per second, depending on solar conditions and latitude. The wind is thin by any terrestrial standard, only a few particles per cubic centimeter even near Earth, but it moves with tremendous velocity and carries the Sun's magnetic field with it, maintaining the heliosphere's structure through sheer kinetic pressure. The termination shock is the first major structural boundary. It marks the distance from the Sun, where the solar wind can no longer maintain supersonic speed against the mounting pressure of the interstellar medium pressing inward. At this point, the wind undergoes a dramatic deceleration, dropping from supersonic to subsonic velocity in a relatively narrow transition zone. The physics is analogous to a sonic boom in reverse. When a jet aircraft exceeds the speed of sound, it creates a shockwave. When the solar wind drops below the equivalent of the local sound speed in the heliospheric plasma, a similar shock structure forms, except this one is spheroidal and wraps around the entire solar system. Voyager 1 crossed the termination shock in December of 2004, at a distance of approximately 94 astronomical units from the Sun. 1 astronomical unit equals the mean distance from Earth to the Sun, about 93 million miles. So Voyager 1 encountered this boundary roughly 8.7 billion miles from home. The crossing was not clean and simple. The spacecraft's instruments recorded multiple shock-like signatures over a period of days, suggesting it crossed and recrossed the boundary as the termination shock rippled back and forth in response to fluctuations in solar wind pressure. The boundary was alive, breathing, flexing in real time as the Sun's output varied. Voyager 2 crossed the termination shock 3 years later, in August of 2007, but at a noticeably different distance, approximately 84 astronomical units. The 10 astronomical unit discrepancy between the two crossings, roughly a billion miles, revealed something important about the heliosphere's geometry. It is not a perfect sphere. The interstellar medium through which the solar system moves exerts greater pressure on the leading edge of the heliosphere, compressing it, while the trailing edge stretches outward into a long tail. The heliosphere is shaped more like a windsock than a soap bubble, deformed by its motion through the local interstellar environment at roughly 26 kilometers per second. What the Voyager instruments recorded at the termination shock confirmed theoretical predictions in some respects and defied them in others. The expected deceleration occurred. Solar wind speed dropped sharply, but the plasma temperature spiked far higher than models anticipated, suggesting that the conversion of kinetic energy into thermal energy at the shock was more efficient than expected. The magnetic field exhibited turbulent fluctuations, indicating the termination shock region was far more dynamic and chaotic than the smooth, clean boundary theorists had envisioned. The real heliosphere, as is so often the case in science, turned out to be messier and more interesting than the model. Beyond the termination shock lies the heliosheath, a thick, turbulent buffer zone where the decelerated solar wind piles up, heats, and churns. If the termination shock is the point where the solar wind slams on the brakes, the heliosheath is the resulting traffic jam. Solar particles in this region no longer race outward in a coherent flow. They slow, compress, heat to millions of degrees, and flow sideways along the inner boundary of the heliosphere, gradually being redirected toward the tail of the bubble, a structure called the heliotail that streams away from the Sun in the direction opposite to our star's motion through the galaxy. The heliosheath is a strange and violent place by the standards of interplanetary space. Magnetic fields become tangled and disordered, losing the clean spiral pattern that characterizes the inner heliosphere. The plasma is choppy, unpredictable, and structured in ways that surprised scientists when the first direct measurements arrived. Voyager 1 spent nearly 9 years traversing this region, from late 2004 to mid-2012, traveling through conditions that no human-made instrument had ever sampled before. During that crossing, both Voyager spacecraft detected something no model had clearly predicted. Regions of enhanced magnetic field strength appeared as discrete structures within the heliosheath, magnetic bubbles roughly 1 astronomical unit across, that formed through instabilities in the turbulent plasma. Scientists described these as a foam of magnetic islands, a frothy zone where the Sun's magnetic field had broken into a chaotic jumble of discrete cells, rather than maintaining any large-scale coherent structure. The heliosheath was not the smooth, gradually changing zone that simple models predicted. It was structured, dynamic, and far more complex than anyone had anticipated from the comfort of theoretical calculations made on Earth. During the long years within the heliosheath, Voyager 1's instruments also tracked the slow evolution of 2 critical measurements: the density of solar origin particles, which had been declining steadily, continued its downward trend. Simultaneously, the flux of galactic cosmic rays, which had been gradually increasing throughout the outer heliosphere, continued to climb. These 2 trends were converging toward a crossover point, a location where solar particles would give way entirely to galactic particles, where the Sun's influence would finally be replaced by the galaxies. The scientists monitoring the data from their offices at the Jet Propulsion Laboratory knew that crossover point had a name: the heliopause, and then it came. The heliopause is the outermost edge of the heliosphere, the surface where the outward pressure of the solar wind finally reaches equilibrium with the inward pressure of the interstellar medium. Cross this line, and you are no longer inside the Sun's magnetic domain. You are no longer surrounded by particles that originated at our star. You have entered a region governed by galactic conditions, where the local interstellar magnetic field replaces the solar magnetic field, where interstellar plasma replaces solar wind plasma, and where galactic cosmic rays arrive undiminished by any solar shielding. Voyager 1 crossed the heliopause on or around August 25, 2012, at a distance of approximately 121 astronomical units from the Sun. That translates to roughly 11.3 billion miles. The crossing was not immediately recognized. Data from the spacecraft arrived on Earth with a lag of approximately 17 hours at the speed of light, and the instruments told a story that required months of careful, sometimes contentious analysis to fully interpret. The confusion arose because different instruments gave seemingly contradictory signals. The cosmic ray detector told a clear story. On August 25th, the count rate of galactic cosmic rays jumped sharply upward, roughly 9% above the already elevated levels measured in the outer heliosheath, and substantially higher than values recorded deeper inside the heliosphere, and the flux of lower energy solar particles dropped to essentially zero. These 2 signatures together painted an unambiguous picture. The spacecraft had left the zone dominated by solar particles and entered the zone dominated by galactic particles. But the magnetometer told a different story, or seemed to. Many models had predicted that the magnetic field direction would rotate substantially at the heliopause, shifting from the Sun's Parker spiral orientation to the interstellar field's orientation. Voyager 1's magnetometer recorded a change in field strength and some shift in direction, but not the dramatic rotation that some theorists expected. This discrepancy fueled months of debate. Had Voyager 1 truly crossed the heliopause, or had it merely entered an unusual region within the heliosheath where solar particles happened to be depleted? The resolution came from an unexpected source. In early 2012, a powerful solar eruption sent a shockwave rippling outward through the heliosphere. Approximately 13 months later, in April of 2013, the disturbance reached Voyager 1's location and caused the thin plasma surrounding the spacecraft to oscillate, producing measurable electron density waves. The plasma wave instrument aboard Voyager 1 detected these oscillations, and crucially, their frequency allowed scientists to calculate the density of the surrounding plasma directly. The density was approximately 0.055 electrons per cubic centimeter, far higher than what would be expected inside the heliosheath, and consistent with the expected density of the local interstellar medium. This measurement settled the debate. Voyager 1 was not in a depleted pocket of the heliosheath. It was in interstellar space. The plasma density confirmed it. The cosmic ray data confirmed it. The only remaining puzzle was why the magnetic field direction had not shifted more dramatically, and subsequent analysis suggested that the interstellar field in our immediate neighbourhood happens to be oriented not too differently from the outer heliospheric field, a coincidence of local geometry rather than evidence against the crossing. Voyager 2 provided even more definitive confirmation when it crossed the heliopause on November 5, 2018, at a distance of approximately 119 astronomical units. Crucially, Voyager 2 carried a functioning plasma science instrument, a device that directly measures the temperature, density, and velocity of the surrounding charged particles. Voyager 1's equivalent instrument had failed in 1980, decades before the heliopause crossing, robbing scientists of the most direct measurement possible for that historic first passage. Voyager 2's plasma instrument delivered beautifully. The data showed a sharp, unambiguous transition. Inside the heliosheath, the plasma was hot, roughly 30,000 to 50,000 Kelvin, and composed predominantly of solar wind protons and electrons flowing outward at reduced speeds. Outside, the plasma temperature dropped, the density increased, and the composition shifted to interstellar material, primarily neutral and ionized hydrogen, originating not from the Sun, but from the broader galactic environment. The change occurred over a remarkably thin boundary, less than 1 astronomical unit in extent. The heliosphere did not fade out gradually. It ended. The transition was a membrane, not a gradient. This sharpness deserves emphasis because it overturns a common misconception. Many people imagine the boundary of the heliosphere as a gradual dimming, a long, slow transition from solar to interstellar conditions unfolding over billions of miles. The Voyager data showed the opposite. The heliopause is thin. The change is crisp. On one side, the Sun rules. On the other, the galaxy takes over. The contrast is stark, measured in different particle populations, different magnetic field configurations, different radiation environments, and it happens within a distance smaller than the gap between Earth and the Sun. Here is where a critical distinction must be made, because it addresses one of the most common misunderstandings about where interstellar space actually begins. When most people hear the term solar system, they think of the Sun and its family of planets, moons, asteroids, and comets. The outermost recognized planet, Neptune, orbits at roughly 30 astronomical units. The Kuiper Belt, home to Pluto and thousands of icy bodies, extends to approximately 50 astronomical units. Beyond that, astronomers believe, lies the Oort cloud, a hypothetical shell of icy objects that may stretch from roughly 2,000 to as far as 100,000 astronomical units from the Sun. Objects in the Oort cloud are still gravitationally bound to our star. They orbit the Sun over periods of millions of years, nudged by the faint gravitational influence of passing stars and the slow tidal pull of the Milky Way itself. This means the solar system, defined gravitationally, extends enormously far, possibly 1 to 2 light years from the Sun in every direction. The heliopause, by contrast, sits at roughly 120 to 140 astronomical units. That is less than 2/100ths of a light year. The heliosphere occupies a tiny fraction of the Sun's gravitational domain, less than 1/10,000th of the volume enclosed by the Oort cloud's outer boundary. This creates a situation that is both physically real and deeply haunting. Objects in the outer Oort cloud are still part of our solar system in the gravitational sense. They still orbit the Sun, but they exist outside the heliosphere, fully immersed in interstellar space. They have no solar magnetic shielding. They are bombarded by the full galactic cosmic ray flux. They drift through interstellar plasma. They are, for all practical environmental purposes, interstellar objects that happen to be gravitationally tethered to a distant star. Their surfaces have been processed by galactic cosmic radiation for billions of years. Their chemical evolution has been shaped by the interstellar medium rather than by the solar wind. They are members of the solar system in name, but residents of interstellar space in reality. Interstellar space, therefore, does not begin at the edge of the solar system's gravitational influence. It begins much closer, at the heliopause, and everything beyond that thin membrane exists in a fundamentally different physical environment, regardless of whether it is still gravitationally attached to the Sun. This distinction matters because it reveals the true nature of the heliopause as a survival boundary rather than an abstract demarcation. The gravitational boundary of the solar system is an imaginary surface where the Sun's pull becomes weaker than a neighbouring star's pull. Nothing physically changes when you cross it. You do not feel it. Your instruments do not register it. It is a mathematical concept, not a physical event. But the heliopause is a real, measurable transition. The magnetic environment transforms. The particle population shifts. The radiation exposure changes. The energy landscape alters. An object crossing the heliopause undergoes a genuine instrument-detectable transformation in its physical circumstances. An object crossing the gravitational boundary notices nothing at all. This is why the Voyager crossings were so scientifically momentous. They were not symbolic milestones or arbitrary lines drawn on a map. They were direct measurements of a real physical transition, the first time any human-built instrument had tasted the interstellar medium and reported back on what it found. What it found was sobering. Beyond the heliopause, the environment reported by both spacecraft confirmed decades of theoretical predictions in their broad strokes, while revealing unexpected complexity in the details. The interstellar plasma was denser than the depleted solar wind at the heliosphere's edge, approximately 0.05 to 0.1 particles per cubic centimetre. The galactic magnetic field was present and oriented roughly as models had predicted, though with fine-scale variations suggesting local turbulence and structure. And the cosmic ray intensity increased to a steady, elevated plateau that showed no sign of decreasing with further distance from the Sun. That last detail carries profound implications. Inside the heliosphere, cosmic ray intensity varies with the solar cycle. When the Sun is active, its stronger magnetic field and denser solar wind more effectively deflect incoming cosmic rays, reducing the flux at Earth. When the Sun is quiet, more cosmic rays penetrate. This variability means the radiation environment inside the bubble is modulated, partially controlled by our star's rhythmic output. Outside the heliopause, that modulation disappears. The cosmic ray flux measured by Voyager 1 after its crossing has remained essentially constant, varying only in response to occasional heliospheric disturbances, propagating outward past the heliopause like ripples from a stone dropped in a pond. The background level is simply the galactic average for our neighbourhood, and it is relentless. There is no quiet period, there is no enhanced shielding phase. The radiation arrives continuously, from every direction, at every moment, without variation and without mercy. It is the steady-state condition of the galaxy, and anything outside a star's protective bubble is exposed to it in full. Voyager 1 and Voyager 2 continue transmitting from this realm as of the mid-2020s, though their power reserves are dwindling steadily. Each spacecraft carries a radioisotope thermoelectric generator fueled by the radioactive decay of plutonium-238. These generators lose approximately 4 watts of electrical output per year as the plutonium decays and the thermoelectric junctions degrade. Scientists at the Jet Propulsion Laboratory have been systematically shutting down instruments to conserve the remaining power for priority measurements. The heaters that protect instruments from the cold of deep space have been turned off one by one. Instruments that still function share power in shifts. The engineering team has performed what amounts to electronic triage, deciding which measurements are worth preserving as the power budget shrinks towards zero. By the mid-2030s, neither spacecraft will have sufficient power to operate any scientific instruments at all. Their transmitters will go silent. The data stream that has connected humanity to these distant explorers for nearly half a century will cease. The last signals, faint beyond anything you could imagine, will fade into the noise floor of the Deep Space Network's receivers, and then there will be nothing. After that, both Voyagers will continue drifting outward through interstellar space as inert metal artifacts. They will carry no active instruments. They will send no signals. But they will carry something else. Each spacecraft bears a golden record, a 12-inch gold-plated copper disc encoded with sounds and images selected to represent the diversity of life and culture on Earth. Greetings in 55 languages. Music from Bach to Chuck Berry. The sound of wind, rain, surf, and birdsong. Photographs of humans, animals, landscapes, and structures. These records were designed as messages to any extraterrestrial intelligence that might someday encounter the spacecraft. The probability of that encounter is, by any honest assessment, vanishingly small. Interstellar space is so incomprehensibly vast that 2 small spacecraft drifting through it without propulsion have essentially zero chance of approaching another star system within any meaningful time frame. Voyager 1 is headed in the general direction of the constellation Ophiuchus and will pass within approximately 1.6 light-years of a star called Gliese 445 in roughly 40,000 years. It will not come close enough for gravitational capture. It will not come close enough for detection by any technology we can currently envision at that star. It will simply drift past, a tiny fleck of metal in an ocean of nothing, carrying a message that no one may ever read. This image captures something essential about the boundary these spacecraft crossed. The heliopause is not just a scientific demarcation, it is the edge of safety. On one side, the sun provides energy, magnetic protection, and a navigational anchor. On the other side, all of that vanishes. The solar wind stops, the magnetic shield drops. The familiar radiation environment is replaced by one that is constant, elevated, and inescapable. The sun itself diminishes from a life-giving furnace to a bright point of light that grows slowly fainter with every passing year, every passing decade, every passing millennium, until it is lost among the millions of other points of light that look exactly the same. Voyager 1 crossed that line at roughly 38,000 miles per hour and kept going. It did not slow down. It did not pause. There was nothing to slow it and nothing to stop for. The interstellar medium offered no resistance worth measuring and no destination worth seeking within any human-relevant time frame. The spacecraft simply continued its trajectory, moving away from the sun at the same speed it had maintained for decades, trading the familiar for the alien with no ceremony and no return. That crossing happened over a decade ago. Since then, Voyager 1 has travelled an additional distance roughly equivalent to the span between the Sun and Uranus. Yet it remains within the immediate vicinity of the heliopause in galactic terms. The nearest star is still over 4 light-years away. At its current speed, even the nearest star would require a journey measured not in centuries but in tens of thousands of years. The spacecraft has been in interstellar space for more than a decade and has traversed an almost negligible fraction of the gap to the nearest neighbouring star. This single fact illuminates the scale of what lies ahead. The heliopause was the doorway. Voyager stepped through it, and on the other side stretches a corridor so long that the doorway itself is already forgotten against the immensity of what comes next. What fills that corridor, what the interstellar medium truly is at the level of atoms and fields and radiation, is a story that defies the simplistic label of empty space and replaces it with something far stranger. There is a word that has haunted our understanding of the cosmos for centuries: empty. It shows up in textbooks, in documentaries, in the casual shorthand of even professional astronomers describing the regions between stars. The void, the vacuum, the blank darkness stretching from one sun to another. This word is not entirely wrong, but it is so catastrophically incomplete that relying on it creates a mental image of interstellar space that misses virtually everything real, everything dangerous, and everything physically consequential about the environment that fills the overwhelming majority of our galaxy. Beyond the heliopause, the region that Voyager entered and confirmed through direct measurement, there exists something. It has density, it has temperature, it has chemical identity, it has magnetic architecture and dynamic behavior that changes over timescales spanning millions of years. Scientists call it the interstellar medium, and understanding what it actually is requires letting go of nearly every assumption your brain carries about what matter should look like, how environments should behave, and what it means for a place to be full or to be barren. Start with the most fundamental physical quantity. How much matter is actually present between the stars? On the surface of Earth, at sea level, every cubic centimetre of the atmosphere surrounding you contains approximately 25 billion molecules. That number, 25 followed by 18 zeros, represents a concentration of matter so thick that molecules slam into each other billions of times per second. This density is what gives air its substance, its resistance, its ability to transmit sound and scatter sunlight into a blue sky. You can feel air against your skin. You can push against it with your hand. It is tangible. It is everywhere. Now leap to the most extreme vacuum conditions that human engineering has ever produced. In specialized laboratory chambers designed for surface science and spaceflight simulation, physicists can reduce particle counts to roughly 100,000 molecules per cubic centimetre. These are the emptiest environments ever manufactured on this planet. Nothing in human industrial or scientific capability can push emptiness further than this. 100,000 particles per cubic centimetre is our technological floor. Now consider interstellar space. In the general diffuse regions filling the volume between stars within the Milky Way, the average particle density is approximately 1 atom per cubic centimetre. 1. A solitary hydrogen atom floating in a volume the size of a sugar cube. In some regions, the density climbs modestly to 10 or perhaps 100 atoms per cubic centimetre near the edges of cold molecular clouds. In others, particularly the vast hot cavities blown open by ancient supernova explosions, the density plunges to 1/100th of an atom per cubic centimetre or even less. At those concentrations, you would need to search through 100 separate sugar cube volumes before encountering a single particle. The ratio between terrestrial atmospheric density and the typical interstellar medium is not a factor of thousands or millions. It is a factor of approximately 25 billion. The gulf is so large that no simple comparison captures it honestly. It exceeds the ratio between a single raindrop and all the water in Earth's oceans. It exceeds the ratio between a human hair's width and the distance from Earth to the Sun. It belongs to that category of numbers that exist comfortably in equations, but refuse to sit comfortably in the human mind. No metaphor captures this gulf. No human experience approximates it. The interstellar medium exists in a state of rarefaction so extreme that it challenges the very definition of the word substance. If you could somehow sweep up all the interstellar gas contained within a cube, 100 kilometers on each side, a volume roughly equivalent to a small European country stacked 100 kilometers high. The total collected material would weigh less than a few milligrams. The entire contents of that enormous region could rest on the tip of a ballpoint pen without registering on any scale you could buy. Yet this near-nothingness is not featureless. It has architecture. It has phases that coexist in a complex and dynamic relationship governed by heating, cooling, and the relentless input of energy from stellar sources throughout the galaxy. Understanding these phases is essential to grasping what the interstellar medium actually is, rather than what the word empty lazily implies. Scientists have identified several distinct states in which the interstellar gas exists, each characterized by radically different temperatures and densities, each occupying a different fraction of the galaxy's volume, and each maintained by different physical processes. The cold neutral medium is, relatively speaking, the densest stable phase of the diffuse interstellar gas. Here, particle concentrations reach 20 to 50 atoms per cubic centimetre, still preposterously thin by any earthly standard, but representing genuine concentrations relative to the surrounding medium. Temperatures in this phase hover around 80 to 100 Kelvin, approximately negative 170 to negative 190 degrees Celsius. Hydrogen atoms in these regions move sluggishly, barely drifting through space. The cold neutral medium tends to organize itself into sheets and filaments and irregular clumps distributed throughout the galactic disk. These cold structures are where star formation ultimately begins. When enough cold gas accumulates in a single gravitational well, the internal thermal pressure can no longer resist the inward pull, and the gas collapses toward the formation of new stellar systems. But this dense, cold phase occupies only a small fraction of the galaxy's interstellar volume, perhaps 2 to 4%. It is the exception within an environment that is already an exception to everyday experience. Far more volumetrically significant is the warm neutral medium. Here, temperatures rise to approximately 6,000 to 10,000 Kelvin, and densities drop to roughly 0.2 to 0.5 atoms per cubic centimetre. Hydrogen, in this phase, remains electrically neutral, each atom retaining its single electron, but the atoms move at considerably higher velocities due to the elevated thermal energy. The warm neutral medium fills an estimated 30 to 40% of the galactic disk's volume, forming the pervasive background through which colder clouds and hotter cavities are scattered. This is the phase that the Voyager spacecraft encountered after crossing the heliopause. The local interstellar cloud, the specific parcel of interstellar gas through which our solar system is currently travelling, consists primarily of warm, partially ionized gas at temperatures near 7,000 Kelvin, with a density of roughly 0.2 atoms per cubic centimetre. It is the interstellar medium's default setting in our cosmic neighbourhood. Hotter and more tenuous still is the warm ionized medium, where temperatures climb to 8,000 to 12,000 Kelvin, and ultraviolet photons from massive young stars have stripped electrons from hydrogen atoms, converting the gas into a plasma of free protons and free electrons. This ionized gas behaves fundamentally differently from its neutral counterpart. Plasma responds to magnetic fields. Its motions generate electrical currents. It emits radiation at characteristic wavelengths, particularly the red glow of hydrogen alpha emission that astronomers can detect across thousands of light years. The warm ionized medium fills roughly 20 to 25% of the galactic disk volume and produces a faint but measurable luminosity spread across the sky, tracing out the distribution of ionized gas throughout the spiral arms and above the galactic plane. But the phase that dominates the galaxy's interstellar volume in the broadest sense is also the most extreme. The hot, ionized medium consists of gas superheated to temperatures of 100,000 to 10 million Kelvin, with some regions exceeding even that staggering figure. Despite these furnace-like temperatures, the density drops to approximately 0.001 to 0.01 atoms per cubic centimetre. This superheated plasma fills enormous cavities within the interstellar medium, regions carved out by the accumulated violence of massive stellar evolution. When a star with a mass greater than roughly 8 times the Sun's mass exhausts its nuclear fuel and collapses, the result is a supernova, an explosion that releases approximately 10 to the 44 joules of kinetic energy into the surrounding interstellar gas. For perspective, this single event liberates roughly as much energy as the Sun will produce over its entire 10 billion year lifetime. The blast wave from the supernova races outward at thousands of kilometers per second, sweeping up interstellar gas like a snowplow, compressing it into a thin, expanding shell and leaving behind an interior cavity of extremely hot, extremely diffuse plasma. These supernova remnants can grow to span dozens of light years in diameter before their expansion stalls, and the hot gas gradually begins to cool and blend back into the ambient medium. In regions where massive stars cluster together, as they frequently do in stellar associations and giant molecular cloud complexes, the combined effects of stellar winds and sequential supernova explosions produce structures on an even grander scale. Superbubbles, as these are called, can extend across several hundred light-years and remain at extreme temperatures for millions of years, continuously reinflated by fresh energy input from the ongoing deaths of massive stars within them. Some models suggest these superbubbles interconnect, forming a network of hot tunnels threading through the galactic disk and creating a pervasive substrate of superheated plasma that accounts for 50 to 70% of the total interstellar volume. Our own solar system resides within one such structure, the local bubble, a region of anomalously low density and elevated temperature, roughly 300 light-years across, that was excavated by a series of supernovae occurring over the past 10 to 20 million years. The temperature structure of the interstellar medium creates one of its most profoundly counterintuitive features. A region at 10 million Kelvin sounds like it should incinerate anything it touches. In terrestrial experience, temperature means heat, means danger, means destruction. Place any object in a 10 million degree environment on Earth and it will be vaporized in a fraction of a second. But temperature in physics measures the average kinetic energy of individual particles, not the total thermal energy delivered to a surface per unit time. When those particles are separated by meters or kilometers, the rate at which they actually strike a surface drops to negligible levels. A spacecraft immersed in the hot, ionized medium would not be heated by its environment. Individual particles would occasionally strike the hull at extraordinary velocities, each one delivering a minuscule amount of energy. But the interval between impacts would be so long, and the energy per impact so small relative to the spacecraft's total thermal budget, that the net effect would be imperceptible. Meanwhile, the spacecraft would radiate its own thermal energy into the surrounding vacuum as infrared photons, losing heat faster than the sparse plasma could replace it. The effective experience would be one of relentless, inescapable cold. In interstellar space, million-degree temperatures and functional freezing coexist in the same cubic meter. The physics is real. The experience is the opposite of what the numbers seem to promise. Woven through every phase of the interstellar medium, connecting them and shaping their behavior at every scale, is a component that receives far less public attention than it deserves: the galactic magnetic field. This field does not originate from a single source. Earth's magnetic field is generated by convective currents in the planet's liquid iron core, a compact dynamo with a well-defined center. The galactic magnetic field arises instead from the collective motions of charged particles throughout the interstellar medium, amplified and sustained by the differential rotation of the Milky Way. The inner regions of the galaxy orbit the galactic center faster than the outer regions. This shearing motion stretches and twists magnetic field lines, continuously regenerating the large-scale field against the natural tendency of turbulence and resistive dissipation to destroy it. The strength of the resulting field is modest. In the general diffuse interstellar medium, measurements indicate typical field strengths of 1 to 5 microgauss. Earth's surface magnetic field, by comparison, measures approximately 500 milligauss. The galactic field is roughly 100,000 to 500,000 times weaker than the field that deflects your compass needle. A common kitchen magnet produces a field millions of times stronger, But the galactic magnetic field extends across light years. It threads through the spiral arms, curves along the disk, loops into the halo above and below the galactic plane. Over distances of parsecs and kiloparsecs, a field measured in microgauss accumulates enormous influence on the behavior of charged particles, the dynamics of gas clouds, and the propagation of one of the most important features of interstellar space, a feature that bears directly on the question of what it would mean to exist beyond the heliosphere. Cosmic rays. These are not electromagnetic rays. The name is a historical artifact from the early 20th century, when the nature of the radiation was still unknown. Cosmic rays are particles, primarily protons, constituting roughly 87% of the total flux, with helium nuclei making up about 12% and heavier ions comprising the remainder. A smaller population of cosmic ray electrons accompanies the nuclear component. These particles have been accelerated to extraordinary energies by astrophysical shock waves, predominantly those generated by supernova explosions rippling through the interstellar medium. The acceleration mechanism is elegant and violent. When a supernova blast wave expands outward, it creates a shock front, a thin boundary where the gas velocity drops abruptly from supersonic to subsonic. Charged particles near this shock front can bounce back and forth across the boundary, gaining energy with each crossing through a process called diffusive shock acceleration. The particle approaches the shock, is deflected by turbulent magnetic fields on one side, crosses the shock, is deflected again on the other side, recrosses, and gains energy at each transit. Over thousands of years of repeated crossings, individual protons can reach energies exceeding 10 to the 15 electron volts, far beyond what any human-built particle accelerator achieves. Once launched into the interstellar medium, these energetic particles begin a long and tortuous journey through the galaxy. They do not travel in straight lines. The galactic magnetic field bends their trajectories, causing them to spiral along field lines, with radii determined by their energy and the local field strength. Lower energy cosmic rays spiral tightly and are strongly affected by magnetic irregularities. Higher energy particles spiral more broadly and are deflected less. But all are scattered by the turbulent magnetic structures that permeate the interstellar medium, randomizing their directions over time. The result of this scattering is that cosmic rays, having originated from point sources like individual supernova remnants, are thoroughly mixed throughout the galaxy within tens of millions of years. They arrive at any given location from essentially all directions simultaneously. Their angular distribution is isotropic to a remarkable degree. You cannot point at a cosmic ray and trace it back to its source, because its path has been scrambled beyond recovery by millions of years of magnetic deflections. The energy spectrum of cosmic rays spans a breathtaking range. At the low end, particles carry energies of a few 100 million electron volts, comparable to protons in a medical cyclotron. At the high end, ultra-high energy cosmic rays exceed 10 to the 20 electron volts, carrying as much kinetic energy in a single proton as a baseball thrown at 60 miles per hour. The flux drops steeply with increasing energy. Low and moderate energy cosmic rays are relatively abundant. The extreme events are extraordinarily rare, but even the moderate energy population, arriving continuously from all directions, represents a steady, unrelenting radiation environment that has no equivalent inside the heliosphere. This is because the heliosphere, as established in the previous part of this story, actively deflects a substantial fraction of incoming galactic cosmic rays. The solar magnetic field and the outward pressure of the solar wind create a barrier that lower energy cosmic rays cannot easily penetrate. During periods of high solar activity, this shielding is enhanced. During solar minimum, it weakens but does not disappear. The effect is measurable and significant. Inside the heliosphere, the cosmic ray flux at Earth is reduced by roughly 30 to 50% relative to the unshielded interstellar value. Beyond the heliopause, that shielding vanishes completely. Both Voyager spacecraft recorded the transition directly. Upon entering interstellar space, Each probe measured a sharp and sustained increase in cosmic ray intensity to a stable plateau that has not varied meaningfully since. The galactic cosmic ray flux in the nearby interstellar medium is constant, isotropic, and permanent. It does not cycle, it does not pulse. It simply is, a steady rain of high-energy particles arriving from every direction at every moment, with no shelter from any star's magnetic output to moderate it. When these particles encounter matter, the results are destructive at the atomic level, and the destruction unfolds through a sequence that is worth understanding in detail because it reveals why shielding against cosmic rays is so fundamentally different from shielding against any other hazard humans have ever faced. Consider a single cosmic ray ion nucleus, a relatively common component of the heavy ion flux, traveling at 95% of the speed of light. This particle is an atom of iron stripped of all 26 of its electrons, a bare nucleus carrying a substantial positive charge and moving with kinetic energy that can exceed 10 billion electron volts. It approaches a spacecraft hull made of aluminum. The moment the iron nucleus enters the aluminum, it begins interacting with the electron clouds of the aluminum atoms it passes through. Its enormous charge and velocity strip electrons from atom after atom along its path, depositing energy in a dense, narrow track. This process, called ionization energy loss, heats the material along the track to extreme temperatures at the molecular scale. In biological tissue, this ionization trail is devastating. It shatters molecular bonds along a corridor only nanometers wide but potentially centimeters long, producing a streak of chemical destruction that cellular repair mechanisms struggle to fix because the damage is so concentrated and so extensive along a single line. But the ionization trail is only the beginning. As the iron nucleus penetrates deeper into the material, the probability increases that it will strike an aluminum nucleus directly. When this happens, the collision is catastrophic for both particles. The aluminum nucleus, containing 27 nucleons, cannot absorb the impact of a relativistic iron nucleus containing 56 nucleons. Both nuclei shatter in a process called spallation. The fragments include free protons, free neutrons, lighter nuclei such as helium, lithium, and beryllium, and unstable particles called pions. The pions decay almost immediately into gamma rays and other particles, producing a burst of electromagnetic radiation at the impact site. The neutrons, carrying no electrical charge, fly outward through the surrounding material without being deflected by electron clouds, penetrating far deeper than charged particles can. These secondary neutrons are particularly dangerous because they interact with other nuclei along their paths, occasionally triggering additional spallation events and creating a branching tree of tertiary particles. The result is called a hadronic cascade. A single incoming iron nucleus can produce hundreds of secondary particles within the first few centimeters of material, and those secondaries can produce hundreds more as they interact with the surrounding atoms. The cascade fans outward and downward through the shielding like a shower, converting one extremely energetic particle into a spray of lower energy particles spread across a wider volume. Some of these secondary particles are more biologically damaging per unit of energy than the original cosmic ray, because they deposit their energy in patterns that are especially difficult for living cells to repair. This is why adding mass to a spacecraft hull does not straightforwardly solve the radiation problem. For lower energy cosmic rays, shielding works as intuition suggests. The material absorbs the particle and the threat is eliminated. But for the high energy heavy ions that dominate the biological risk in the galactic cosmic ray flux, thicker shielding can actually increase the total radiation dose experienced on the interior side of the hull. The incoming particle is stopped, but the cascade it generates delivers a more diffuse and in some respects more harmful radiation field to anything sheltering behind the shield. Optimal shielding strategies involve materials rich in hydrogen, such as water or polyethylene, which produce fewer heavy secondary fragments when struck by cosmic rays. But even these materials provide diminishing returns beyond a certain thickness, and the mass penalty of carrying sufficient shielding for a decades-long voyage adds enormously to the propulsion and energy requirements that already strain the boundaries of the possible. There is one more component of the interstellar medium that deserves attention: not because it dominates by mass or volume, but because its effects are disproportionate to its minuscule abundance: interstellar dust. These are not the dust motes visible in a beam of sunlight. Interstellar dust grains are microscopic solid particles, typically measuring between a few nanometers and a few tenths of a micrometer in diameter. Smaller than a wavelength of visible light, they are composed primarily of silicate minerals and carbonaceous compounds, essentially tiny fragments of rock and soot. Their origin lies in the outer atmospheres of evolved stars, particularly red giants and asymptotic giant branch stars, where conditions of temperature and density allow solid particles to condense from cooling stellar outflows. Supernova explosions also produce and distribute dust, seeding the interstellar medium with freshly forged solid material. The number density of interstellar dust is almost absurdly low. In the diffuse interstellar medium, a typical figure is roughly 1 grain per 100,000 cubic meters, one microscopic speck drifting alone in a volume the size of a large residential building. Yet these vanishingly sparse particles produce effects that shape the observational history of astronomy and the chemical evolution of the galaxy. Dust absorbs and scatters visible light. This property is responsible for the dark lanes and rifts visible in images of the Milky Way. The prominent dark band splitting the glowing arch of our galaxy's disk as seen from Earth is not a gap in the distribution of stars. It is a curtain of interstellar dust lying between us and the billions of stars beyond, absorbing their visible photons and re-radiating the energy at infrared wavelengths invisible to the human eye. For over a century, this extinction of starlight by dust confused astronomers, leading them to underestimate galactic distances and misinterpret the structure of the Milky Way. Only with the development of infrared and radio astronomy, wavelengths to which dust is largely transparent, could scientists see through the veil and map the galaxy's true structure. Dust also serves as the galaxy's chemical workshop. In the incredibly sparse conditions of interstellar space, atoms drifting through the gas phase encounter each other so rarely that chemical reactions between them proceed at negligible rates. Two hydrogen atoms passing within reactive distance of each other in the diffuse medium might wait millions of years for the encounter to happen. But when an atom lands on the surface of a dust grain, it can stick, migrate across the surface, and encounter other adsorbed atoms with which it can react. The grain surface acts as a meeting place and a catalyst, dramatically accelerating reactions that would be impossibly slow in the gas phase alone. The most important of these grain surface reactions is the formation of molecular hydrogen. Two hydrogen atoms adsorbed on a dust grain surface can combine into a molecule of H2, which then desorbs back into the gas. This process is the primary pathway by which molecular hydrogen forms in the interstellar medium. Without dust grains facilitating this reaction, the galaxy's supply of molecular hydrogen, the essential fuel for gravitational collapse and star formation, would be drastically lower. Dust grains, despite their almost unimaginable scarcity, are indispensable to the galaxy's ability to form new stars. The chemical inventory of interstellar space extends well beyond molecular hydrogen. As of the mid-2020s, astronomers have identified over 270 distinct molecular species in interstellar and circumstellar environments. Simple diatomics like carbon monoxide and hydroxyl radical are common in many phases of the medium. More complex molecules, including formaldehyde, methanol, acetaldehyde, and even amino acid precursors like glycine, have been detected in cold, dense molecular clouds where temperatures drop below 20 Kelvin and densities climb above several thousand particles per cubic centimeter. Polycyclic aromatic hydrocarbons, large carbon ring structures, appear to be ubiquitous throughout the diffuse medium, producing characteristic infrared emission features that astronomers detect across the galaxy and beyond. This molecular richness is concentrated overwhelmingly in the cold, dense phase. In the warm and hot phases that fill most of the interstellar volume, ultraviolet radiation from nearby and distant stars dissociates molecular bonds within timescales of a few 100,000 years. Only the hardiest molecules persist in exposed diffuse conditions, primarily carbon monoxide, which is shielded by its own abundance through a process called self-shielding, and molecular hydrogen in regions where even modest dust columns provide protection from photodissociation. The general diffuse interstellar medium between stars is chemically sparse, a thin broth of atoms and atomic ions with occasional molecular survivors and scattered microscopic dust grains. This, then, is what fills the space between stars, not nothing, not the featureless void of popular imagination. It is a dynamic, layered, magnetically threaded, radiation-saturated, chemically active medium with temperature extremes spanning 5 orders of magnitude, density variations covering 4 orders of magnitude, solid particles catalyzing molecular formation on their microscopic surfaces, and high-energy particles streaming through every cubic centimetre at nearly the speed of light. It has physics, it has chemistry, it has structure at scales ranging from the submicrometer dimensions of individual dust grains to the 100-parsec spans of supernova-carved superbubbles. It is a subject that fills journals and sustains entire research careers. Telescopes across the electromagnetic spectrum, from radio dishes to gamma-ray observatories, are devoted to studying its properties. And none of this changes the fundamental practical reality. 1 atom per cubic centimetre is not a resource. It is the ghost of a resource. A magnetic field of a few microgauss threading through light years of vacuum is not a shield. It is a structural feature of the void itself. Dust grains separated by distances larger than concert halls are not raw material. They are isolated motes adrift in a desert that makes the Sahara look like an ocean. Cosmic rays arriving from every direction at every moment are not an inconvenience. They are an unceasing assault with no shelter anywhere in the medium capable of stopping them. The interstellar medium is one of the great paradoxes of physical science. It is simultaneously fascinating and useless, rich in phenomena and devoid of anything an organism or a machine could exploit. It is an ocean with no water you could drink, a landscape with no ground you could stand on, a sky with no air you could breathe. It is there. It is real. It has been studied for a century and will be studied for centuries more. But for anything attempting to cross it, to survive within it, to use it as a medium of travel rather than a subject of remote observation, the interstellar medium offers precisely nothing. Its phases and structures and magnetic fields and molecular species are irrelevant to the traveller. What matters is the absence of usable matter, the absence of harvestable energy, the absence of shielding, the absence of landmarks, way stations, or any feature that could serve as a resource rather than a hazard. The interstellar medium is not empty in the way a layperson imagines, but it is barren in a way that is, if anything, worse than true emptiness. Because true emptiness would at least be simple. The interstellar medium is complex, structured, and actively hostile. A thin stew of radiation and magnetism and near vacuum that extends for light years in every direction without offering a single handhold to anything passing through. What this barrenness means, when combined with the staggering distances that separate one stellar system from the next, is a question that transforms the interstellar medium from a scientific curiosity into something far more consequential, a barrier so vast and so featureless that crossing it challenges the limits of physics itself. Knowing the composition of interstellar space and understanding what it means to exist within it are 2 fundamentally different things. Everything described so far about the interstellar medium has been the language of a physicist, cataloguing phases, measuring densities, tracing magnetic architecture. All of that is accurate. All of it matters scientifically. But none of it answers the question that actually haunts the human imagination when we look up at the night sky and wonder about the stars. Could we ever get there? Could anything get there? And if not, why not? The answer is not a simple no. It is something worse than no. It is a cascading series of physical constraints, each one independently daunting, that combine to produce a barrier so comprehensive that it challenges the limits of what any technology, no matter how advanced, could plausibly overcome. Interstellar space does not block travel with a wall. It blocks travel with distance, deprivation, and time, the three most patient adversaries in all of physics. Begin with what happens to anything that leaves the heliosphere and attempts to persist in the interstellar medium without the protection of a star. Inside the solar system, energy is abundant. Sunlight floods the inner planets with a generous and reliable power source. At Earth's orbital distance, the solar flux delivers approximately 1,360 watts per square meter. A surface the size of a dining table, aimed directly at the sun, receives enough energy to power a small home. Even at Jupiter, 5 times farther from the sun, solar panels can still generate meaningful electricity. The Juno spacecraft operates entirely on solar power at Jovian distances, a testament to how far solar engineering has advanced. But solar intensity obeys the inverse square law. Double your distance from the sun and the flux drops to 1/4. Triple the distance and it falls to 1/9. By the orbit of Neptune, roughly 30 astronomical units from the sun, solar flux has diminished to approximately 1/900th of its value at Earth. Still technically usable with very large arrays, but marginal. By the heliopause at 120 astronomical units, the flux has fallen to less than 1/14,000th of what Earth receives. And these are still distances measured within the heliosphere, still cosmically trivial compared to the gaps between stars. At 1 light-year from the sun, the solar flux has diminished to roughly 1/4 billionth of its value at Earth, amounting to a few 10 millionths of a watt per square meter. To generate even a single watt of electricity from sunlight at this distance, even with optimistic panel efficiency, you would need a solar array with a collection area exceeding tens of millions of square meters, an expanse rivaling the footprint of a major international airport, just to power a single light bulb. At the distance of the nearest star, over 4 light-years away, the sun would appear as nothing more than a moderately bright star in an unfamiliar sky. Its energy contribution to any spacecraft in the vicinity would be indistinguishable from zero. This creates a problem that has no analogue in the history of human exploration. Every previous journey undertaken by our species has occurred within an environment that offered at least some possibility of sustaining the traveller along the way. Ocean voyagers could fish. Arctic explorers could hunt seals. Even astronauts in low Earth orbit receive abundant solar energy and can be resupplied from the surface within hours. The fundamental assumption underlying every expedition in human history is that the environment through which you travel, however hostile, contains something you can use. Food, water, energy, raw materials, shelter, something. Interstellar space contains nothing you can use. The solar wind that powered your departure has ceased. The sunlight that energized your instruments has faded to irrelevance. The interstellar medium surrounding you, 1 atom per cubic centimeter of thin hydrogen gas, cannot be collected in useful quantities, cannot be burned, cannot be fused without infrastructure so massive it defeats the purpose. You are moving through a region that is not merely inhospitable, it is inert. It offers precisely zero assistance to anything passing through it. This means that any vehicle travelling through interstellar space must carry its own energy supply from departure to arrival. There is no recharging. There is no topping off. Whatever energy the spacecraft carries when it leaves the solar system is all it will ever have, minus whatever it loses to inefficiency and entropy along the way. Current spacecraft use radioisotope thermoelectric generators for deep space missions. These devices convert the heat from radioactive decay of plutonium-238 into electricity. They are reliable, long-lived, and independent of sunlight, but they are not eternal. The plutonium decays, the thermoelectric materials degrade. Output drops by roughly 4 watts per year for the generators aboard the Voyager spacecraft. Within decades, the output becomes insufficient to power even basic instruments. Within a century, the generator is functionally dead. Nuclear fission reactors offer more power for longer durations, and designs for space-rated fission systems have existed since the 1960s. The Soviet Union flew over 30 fission-powered spacecraft during the Cold War, and NASA has periodically revisited reactor concepts for deep space applications. But even fission fuel is finite. A reactor sized for a modestly powered spacecraft might operate for decades, perhaps a century with careful fuel management. It cannot operate for millennia, and the distances between stars demand millennia of travel time at any speed currently achievable by human engineering. The energy deficit extends beyond mere electrical power. Propulsion itself requires energy, and the energy requirements for interstellar travel are not merely large. They are functionally absurd by current technological standards. Consider the most basic version of the problem. The nearest star system to our Sun is Alpha Centauri, located approximately 4.24 light-years away. 1 light-year equals roughly 5.88 trillion miles. The total distance to Alpha Centauri is therefore approximately 25 trillion miles. Voyager 1, the fastest human-made object on an outward trajectory from the Sun, travels at roughly 17 kilometers per second, or about 38,000 miles per hour. At this speed, the journey to Alpha Centauri would require approximately 73,000 years. 73,000 years. When that journey would have begun, anatomically modern humans were painting on cave walls in Europe and sharing the continent with Neanderthals. Every civilization that has ever risen and fallen on Earth, every empire, every religion, every scientific revolution, every war, every work of art, fits comfortably within that travel time with room to spare. The entire recorded history of humanity, roughly 5,000 years, represents less than 7% of a single trip to the nearest star at our current best speed. What about faster? The Parker Solar Probe, during its closest approaches to the Sun, reaches speeds of approximately 192 kilometers per second, making it the fastest human-made object ever relative to the Sun. If a spacecraft could somehow maintain that extraordinary velocity on an outward interstellar trajectory, the trip to Alpha Centauri would still take approximately 6,600 years. The ancient Sumerians were inventing cuneiform writing roughly that long ago. An entire arc of human civilization would pass before the spacecraft arrived. To bring the travel time down to anything remotely approaching a human lifetime requires velocities that are, by current engineering standards, almost inconceivably fast. At 10% of the speed of light, roughly 30,000 kilometers per second, the crossing to Alpha Centauri would take approximately 42 years. A crew departing in their 20s might arrive in their 60s, demanding, but not impossible in principle for a single generation. At 20% of the speed of light, the trip shrinks to roughly 21 years. Almost manageable if everything else about the mission could be solved. But achieving these speeds requires energy inputs that dwarf anything humanity has ever produced for a single purpose. The kinetic energy of a moving object scales with the square of its velocity. Double the speed and you quadruple the required energy. To accelerate a modest 1,000 kilogram payload, roughly the mass of a small car, to 10% of the speed of light, requires approximately 4.5 times 10 to the 17 joules of kinetic energy. This is equivalent to roughly 107 megatons of TNT, more than twice the yield of the most powerful nuclear weapon ever detonated, the Soviet Tsar bomber, and that calculation accounts only for the payload itself. It ignores the mass of the propulsion system, the fuel, the shielding, the life support systems, and the structural framework required to hold everything together. It also ignores the energy needed to decelerate at the destination, which for a conventional rocket doubles the total fuel requirement through the tyranny of the rocket equation. For a crewed vessel with enough mass to sustain human life for decades, the energy requirements escalate by orders of magnitude. A ship massing 100,000 kilograms, modest by the standards of any crewed vessel that could plausibly support a crew for 40 years, would need kinetic energy equivalent to tens of thousands of megatons of TNT to reach 10% of light speed. The total energy output of human civilization in an entire year is roughly 5.8 times 10 to the 20 joules, Accelerating a single, modestly sized starship to a useful interstellar velocity would consume a significant fraction of global annual energy production, concentrated into a single act of propulsion. These figures assume perfect efficiency, which no real propulsion system achieves. Chemical rockets, the workhorses of current spaceflight, have exhaust velocities of a few kilometers per second, hopelessly inadequate for interstellar speeds. Ion drives, which use electrically accelerated plasma, achieve higher exhaust velocities but produce minuscule thrust, requiring decades of continuous operation to build up even modest velocities. Nuclear thermal rockets improve on chemical performance but still fall far short of what interstellar distances demand. Nuclear pulse propulsion, the concept of detonating nuclear bombs behind a spacecraft and riding the blast waves, could theoretically reach a few percent of light speed, but requires thousands of nuclear detonations and raises engineering challenges that have never been addressed beyond preliminary studies. Fusion propulsion, if it could be made to work, offers the most plausible path to interstellar speeds. Fusing deuterium and helium-3, for example, releases energy with an efficiency roughly 100 times greater than fission. A fusion-powered spacecraft could theoretically reach 5 to 10% of light speed, with a fuel-mass ratio that is demanding but not physically absurd. The problem is that controlled fusion propulsion does not exist. Humanity has been working on controlled fusion power for over 70 years and has yet to produce a sustained net energy gain in a terrestrial reactor, let alone a compact, reliable engine suitable for a spacecraft. The Bussard ramjet, conceived in 1960, proposed an elegant workaround. Instead of carrying fuel, the spacecraft would scoop hydrogen from the interstellar medium itself, funneling it into an onboard fusion reactor. The concept is seductive. If it worked, the spacecraft could accelerate continuously without ever running out of fuel, drawing sustenance from the very medium it travelled through. The physics demolishes this vision. At a typical interstellar density of 1 atom per cubic centimetre, collecting 1 gram of hydrogen per second requires a scoop with a frontal cross-section of tens of thousands of square kilometres. The engineering challenge of constructing and deploying a magnetic funnel of this scale is, to put it diplomatically, unsolved. Worse, detailed calculations performed in the decades following Bussard's original proposal revealed that the drag produced by interacting with even this extremely thin medium at relativistic speeds likely exceeds the thrust generated by fusing the collected hydrogen. The interstellar medium is too sparse to serve as fuel and too present to ignore as an obstacle. The ramjet becomes a brake. Even setting aside the propulsion problem, the journey itself presents hazards that compound over the immense timescales involved. Cosmic radiation pervades interstellar space at its full galactic intensity, the unshielded flux of the entire galaxy arriving from every direction simultaneously. Inside the heliosphere, the Sun's magnetic field deflects a meaningful fraction of lower energy cosmic rays. Beyond the heliopause, that deflection disappears entirely. Any spacecraft or crew exposed to the unshielded interstellar cosmic ray flux faces a continuous radiation dose that accumulates relentlessly over the years and decades of transit. For biological organisms, this exposure is serious. Galactic cosmic rays include heavy ions, nuclei of elements like carbon, oxygen, silicon, and iron, accelerated to relativistic speeds. When these heavy ions pass through biological tissue, they deposit energy along dense, concentrated tracks that cause clustered DNA damage, far more severe than what lower mass particles produce. This type of damage is difficult for cellular repair mechanisms to fix correctly, leading to elevated rates of mutation, cancer, and degenerative tissue effects. Studies of radiation exposure in astronauts aboard the International Space Station, which orbits within the partial protection of Earth's magnetosphere, already show measurable biological effects from cosmic ray exposure over periods of months. Interstellar transit times measured in decades would magnify these effects enormously. Shielding helps, but cannot solve the problem at its root. The secondary cascades that a single cosmic ray triggers inside hull material mean that no practical thickness eliminates the threat. Better materials exist, and they reduce the dose measurably. But they do not eliminate it, and every kilogram of protective mass added to the spacecraft is a kilogram that must also be accelerated to interstellar velocities, compounding the already staggering energy requirements. Radiation protection and propulsion are locked in a zero-sum competition for mass budget, and the cosmic ray flux tips the balance against both. For electronic systems, the situation is somewhat more manageable but still significant. Radiation-hardened electronics can tolerate higher doses than biological tissue, but they are not immune. Over decades, cumulative radiation damage degrades semiconductor performance, increases error rates, and reduces the reliability of computational systems. A crewed interstellar vessel would require not just radiation-hardened primary systems, but redundant backups and the ability to repair or replace damaged components over the lifetime of the mission using only the materials and tools carried aboard. Now add the most psychologically devastating feature of interstellar travel, the absolute absence of any stopping point along the way. Within the solar system, destinations are distributed at intervals that, while vast by human standards, are at least conceivable. Mars is a few months away, Jupiter a few years. Even the outer planets are reachable within a human lifetime using current technology. Along the way, there are objects to study, gravitational assists to exploit, and at least the theoretical possibility of emergency diversions. The solar system is sparse by terrestrial standards but populated by galactic ones. Interstellar space offers nothing comparable. Between our solar system and the Alpha Centauri system, there are no planets, no asteroids, no comets, no stations, no objects of any kind that could serve as a waypoint, a refuge, or a resource depot. The Oort cloud, if it exists as theorized, may extend outward from our Sun for a light year or perhaps two. Objects within it are icy bodies, small and widely scattered, gravitationally bound to our star. They are not clustered conveniently along departure trajectories. They are distributed across an enormous spherical shell, with typical separations of billions of miles between individual objects. Even if a departing spacecraft happened to pass near an Oort cloud body, the encounter would be fleeting, and the object itself would offer little of practical value, a dirty snowball a few kilometers across tumbling through the darkness. Beyond the Oort cloud lies the true desert. The space between our Sun's outermost gravitational hangers-on and the equivalent boundary of the Alpha Centauri system is a region that current astrophysical models predict contains no solid body of any meaningful size. No rogue planets have been confirmed in this specific gap, though statistically some may drift through interstellar space in the broader galactic neighborhood. No asteroids, no comets unbound from any star, no debris of any kind that a traveler could count on finding along the route. The interstellar medium itself, at 1 atom per cubic centimeter, provides nothing to work with. For a stretch of approximately 2 to 3 light years, depending on how far each star's Oort cloud extends, the journey passes through a region that is, as far as we know, entirely featureless. Try to imagine what this featurelessness would look like from inside a spacecraft. In the early months of the journey, the sun would still be the brightest object in the sky behind you, gradually dimming but recognizable. Alpha Centauri would brighten slowly ahead, but perceptibly only over years. Between those two reference points, the star field would remain essentially static. No object would approach. No object would recede at a rate visible to the human eye. No landmark of any kind would break the monotony. A crew member looking out a viewport on day 100 of the journey would see the same stars in the same positions as on day 1000. The visual environment would be indistinguishable from a high-resolution photograph taped over the window. Nothing moves, nothing changes, nothing happens. This sensory deprivation would persist for years. Even at 10% of light speed, the most optimistic plausible cruise velocity, the crossing to Alpha Centauri takes over 4 decades. For the vast majority of that time, the surrounding environment provides zero visual feedback of progress. human brains are wired to interpret stillness as stagnation. Our sense of journey depends on changing scenery, passing landmarks, the feeling of covering ground. Interstellar space provides none of these cues. A crew that has been travelling for 10 years at blistering speed would look out the window and see a sky that appears identical to the sky they saw when they departed. The psychological toll of this unrelenting sameness, sustained over decades in a confined vessel with no option for shore leave, no possibility of turning back, and no guarantee that the destination will prove hospitable, is a challenge that no human expedition has ever confronted at anything remotely approaching this scale. No stopping points also means no resupply. Every molecule of water, every kilogram of food, every replacement component, every calorie of energy required for the entire voyage must be aboard the vessel when it departs. There is no option to refuel, restock, or repair using external resources. A malfunction in deep interstellar space cannot be addressed by a rescue mission. The nearest help is light years behind you and light years ahead. The concept of emergency, which in every other context of human experience implies the possibility of rescue, or at least retreat, becomes meaningless in interstellar space. There is no rescue, there is no retreat. There is only forward, into more of the same emptiness, for years or decades, with whatever you brought with you and nothing else. The communication situation compounds the isolation in ways that evolve cruelly over the course of a voyage. At launch, a spacecraft departing the solar system would maintain near real-time communication with Earth. Delays would be measured in hours, comparable to current deep space missions. Conversations would be slow but functional. Mission controllers could respond to questions, provide guidance, upload software patches, and offer the psychological comfort of a connected link to home. But the delay grows with distance, and it grows at the speed of light, which is the fastest any signal can travel. At 1/10 of a light year from Earth, roughly the distance at which the sun's Oort cloud might begin to thin out, the one-way communication delay would be approximately 37 days. A question sent to Earth would receive a response more than 2 months later. Already, conversation has degraded to correspondence. Mission control can still offer advice, but it arrives too late to help with any time-sensitive decision. At 1 light year, the delay reaches 1 year in each direction, a 2-year round trip for a single exchange. At this distance, communication with Earth resembles the exchange of letters between continents in the 18th century, except each letter takes a year to arrive rather than months. The emotional connection to home weakens. The crew knows that the people they are communicating with have aged a year between question and answer. Events on Earth that were current when the message was sent are ancient history by the time the reply arrives. At 2 light years, the midpoint of a crossing to Alpha Centauri, the round-trip delay exceeds 4 years. A child born on Earth when a message was sent would be starting school by the time the reply reached the spacecraft. The conversation has not merely slowed, it has ceased to function as conversation in any meaningful sense. The crew could still transmit reports, Earth could still transmit encouragement, news, and cultural updates, but the exchanges would be monologues, each party speaking into a void and waiting years for an echo that arrives stripped of all immediacy and relevance. Signal strength deteriorates alongside delay. Radio transmissions weaken with the square of distance. A signal that is comfortably detectable at 1 astronomical unit becomes 10,000 times fainter at 100 astronomical units and billions of times fainter at interstellar distances. The Deep Space Network, NASA's array of massive radio dishes used to communicate with interplanetary probes, can maintain contact with spacecraft at the heliopause, only because the spacecraft carry relatively powerful transmitters and the ground stations use antennas up to 70 meters in diameter. At interstellar distances, even these systems would struggle. Maintaining a data link at 1 light year would require either vastly more powerful transmitters aboard the spacecraft, consuming precious energy reserves, or vastly larger receiving arrays on Earth, spanning kilometers rather than meters. Communication does not become impossible at interstellar distances, but it becomes expensive, slow, and functionally one-directional over the timescales relevant to a voyage. By the final years of a crossing, a crew would exist in a state of communicative isolation unprecedented in human experience. Messages from Earth would arrive years after they were sent, carrying news of a world that has moved on without them. Replies sent from the spacecraft would not reach Earth until years after the voyage had ended, one way or another. The crew would, for all practical purposes, be alone. Not alone in the romantic sense of an explorer on a remote mountain. Alone in the absolute sense of being the only conscious beings within light years in any direction, separated from every other human by a gulf of space and time that no signal can bridge quickly enough to matter. All of these constraints, energy, radiation, isolation, sensory deprivation, communication decay, absence of resources, apply to the simplest possible interstellar crossing, a trip to the single nearest star. The distances to other stars escalate rapidly, and the compounding of every difficulty makes each additional light year qualitatively more punishing than the last. Within 10 light years of the Sun, there are approximately 12 known star systems. Some are single stars, others are binary or triple systems. The average spacing in this immediate neighborhood is a few light years, which is relatively dense by galactic standards, because we happen to sit within a moderately populated region of the Orion Spur, a minor structural feature between larger spiral arms. But even within this relatively cozy neighborhood, the difficulty of reaching specific targets varies enormously. Alpha Centauri at 4.24 light-years is the closest. Barnard's star at 5.96 light-years is the next nearest single star. Wolf, 359, at 7.86 light-years. Lalande, 2.1185 at 8.31. Sirius at 8.6. Each additional light-year of distance does not simply add a proportional amount of travel time. It compounds every challenge simultaneously. A voyage to Barnard's star at 10% of light speed would take roughly 60 years instead of 42. Those extra 18 years demand 18 additional years of food, water, air, and energy. 18 more years of cosmic ray exposure. 18 more years of material degradation, mechanical wear, and electronic fatigue. 18 more years of psychological endurance in a confined, unchanging environment. 18 more years during which any single point failure in a critical system could prove fatal with no possibility of external assistance. At 10 light-years, the pool of accessible stars expands modestly, but the transit times stretch to a century, 100 years aboard a spacecraft. No human being has ever lived that long, let alone lived that long inside a metal vessel hurtling through a radiation-saturated vacuum. A journey of this duration would require either technologies that do not currently exist, such as reliable suspended animation, or a fundamental reconception of the mission as a generational endeavour, a vessel designed not for a crew that departs and arrives, but for a population that lives and dies aboard the ship, with their descendants completing the voyage. Generational ships introduce their own cascade of difficulties. Maintaining a stable, functional society for a century or more within a closed environment with finite resources and zero external input is a social engineering challenge without precedent. Every calorie must be produced on board through agriculture or recycling. Every berth must be balanced against available resources. Every dispute must be resolved without the option of anyone leaving. The ship becomes a world unto itself, a sealed terrarium that must sustain human civilization across multiple generations while travelling through a void that offers no help and no forgiveness for mistakes. At 20 light-years, the transit time at 10% of light speed reaches 2 centuries. At 50 light-years, 5 centuries. At 100 light-years, a millennium. These are not distances to obscure stars in remote corners of the galaxy. These are distances to the nearest few thousand stellar neighbours in our own arm of the Milky Way. The galaxy itself spans 100,000 light-years. At 10% of the speed of light, crossing it would take 1 million years. Even at the speed of light, a physical impossibility for any massive object, the crossing would require 100,000 years, a span roughly equal to the entire existence of anatomically modern humans on Earth. Each step outward along this ladder of distance deepens the isolation and multiplies the hostility. A ship travelling to a star 50 light-years away would spend 5 centuries in the interstellar medium, 500 years of cosmic ray bombardment, 500 years of equipment aging, 500 years of recycling the same water, the same air, the same finite stock of materials, 500 years during which a message sent home would not receive a reply for a century. The crew that departed would be ancestors, mythological figures to the descendants who eventually arrived, if anyone arrived at all. And the character of the medium through which the ship travels never changes. It is the same 1 atom per cubic centimetre at 50 light-years as it is at 4, the same cosmic ray flux, the same magnetic field, the same absence of shelter, landmarks, and resources. The interstellar medium does not become more hospitable at greater distances. It does not offer oases or rest stops or regions of enhanced density where a traveller might pause and gather strength. It is uniform in its barrenness across spans of space that encompass millions of potentially habitable worlds, each one separated from its neighbours by this same implacable desert. The galaxy is large enough that interstellar space transforms from a challenge into a cage. The distances are not merely inconvenient, they are isolating in a structural sense. Each star system exists within its own tiny sphere of warmth, energy, and protection, surrounded on all sides by a medium that offers nothing to anything attempting to bridge the gap. The gaps are not just wide, they are empty, and the combination of width and emptiness creates a barrier that is qualitatively different from any obstacle that speed or cleverness can straightforwardly overcome. This is the nature of the hostile desert that fills the galaxy between its stars. It has no defences because it needs none. Its weapon is not force but absence, the slow accumulation of nothing over distances so vast that time itself becomes the enemy. Light year after light year, it offers no sustenance, no reprieve, no change in conditions, only the steady compounding of distance, radiation, and deprivation over spans of time that mock human lifetimes, human engineering and human patience. The medium itself is thin, the distances are not, and it is the distances, amplified by the barrenness of the medium, that transform interstellar space from an empty corridor into something far more formidable, a barrier that may define the fundamental character of the galaxy itself. What remains to be understood is the most unsettling realization of all. This barrier is not an anomaly within the Milky Way. It is not a localized desert between a few unfortunate stars. It is the dominant physical feature of the entire galaxy, and what it reveals about the true nature of our cosmic home challenges everything we think we see when we look up at the night sky. Step back now from the spacecraft and the engineering and the calculations of energy and velocity. Forget for a moment the question of whether humans could ever cross the interstellar void. Set aside the radiation dosimetry and the fuel mass ratios and the travel times measured in millennia. Instead, ask something more fundamental, something that does not depend on technology or ambition or cleverness. Ask what the Milky Way actually is, physically, when measured not by its luminous highlights but by its total volume. The answer to this question is the most important thing in this entire story, because it reveals that interstellar space is not an unfortunate obstacle between the interesting parts of the galaxy. It is the galaxy. The stars are decoration. The void is the substance. And understanding this inversion, truly absorbing what it means, changes the way every photograph of the night sky should look to you forever. Begin with the dimensions. The Milky Way's disk spans roughly 100,000 light-years in diameter and averages approximately 2,000 light-years in thickness. This disk is where the majority of stars, gas and dust concentrate, the visible architecture of spiral arms and dense stellar neighbourhoods that fills the images in every astronomy textbook. Above and below the disk extends the galactic halo, a diffuse spherical region populated by ancient globular clusters, scattered individual stars and an enormous envelope of dark matter. The halo extends outward to at least 130,000 light-years from the galactic center, possibly much farther depending on how the boundary is defined. Even confining the analysis to the disk alone and ignoring the halo, the total volume is staggering. A cylinder, 100,000 light-years across and 2,000 light-years thick, contains roughly 15 billion cubic light-years of space. The halo adds substantially more. Including, it brings the total galactic volume to something in the range of several trillion cubic light-years, though the precise figure depends on where you draw the outer boundary of a structure that fades gradually rather than ending sharply. Now consider how much of that volume is occupied by stars. Our Sun is a fairly typical star with a diameter of roughly 860,000 miles. Converting to light-year units, that diameter is approximately 0.00000015 light-years. Even the largest known supergiants, bloated red stars like UY Scuti or Stephenson 218, measure only a few billion miles across, still a negligible fraction of a light-year. Stars are extraordinarily small relative to the spaces that separate them. In the solar neighborhood, the average distance between adjacent stars is roughly 4 to 5 light-years. Each star occupies, on average, a private volume of approximately 7 to 8 cubic light-years. Within that volume, the star itself, even a generous estimate of its physical size, fills a fraction so small that expressing it requires scientific notation. The ratio of a typical star's volume to the volume of the space it occupies is on the order of 1 part in 10 to the 22nd power. Written out, that is a 1 preceded by a decimal point and 21 zeros. It is roughly the same ratio as a single marble compared to the volume of the entire Earth. Scale this across the entire galaxy and the picture becomes overwhelming. If you could somehow sum up the volume of every star in the Milky Way, all 200 to 400 billion of them, the total stellar volume would occupy less than 1/billionth of 1% of the galaxy's total volume. The rest, the other 99.9999999%, is interstellar space. Gas at 1 atom per cubic centimeter, magnetic fields at a few microgauss, cosmic rays streaming silently in every direction, dust grains separated by distances larger than city blocks. The thin, hostile, functionally barren medium that this entire story has been describing. The galaxy is not a city of stars with gaps between them. It is an ocean of interstellar medium with stars scattered through it like grains of pollen drifting across a lake. The grains are real. The lake is what defines the environment. If you were to select a random point anywhere within the Milky Way's volume, the probability of that point falling inside a star, or even within an astronomical unit of a star, is so close to zero that for all practical purposes, it would never happen. The overwhelming likelihood is that your randomly chosen point would land in interstellar space, surrounded by near vacuum in every direction, with the nearest star a dim point of light several light-years away. This statistical reality is obscured by the way humans observe the galaxy. When we look at the Milky Way stretching across the night sky, we see stars, thousands of them to the naked eye, billions through telescopes. The visual impression is one of abundance, even crowding. The galactic disk appears to overflow with luminous points packed shoulder to shoulder in a glowing band, but this impression is a projection artifact. We are collapsing a 3-dimensional structure thousands of light-years deep into a 2-dimensional image on the inside of our retina. Stars that are separated by enormous gulfs of empty space appear to overlap when viewed along the line of sight through the disk. The apparent density is an illusion created by the geometry of observation. If you could somehow view the galaxy from outside, from a vantage point millions of light-years away, and if your eyes could resolve individual stars, the truth would be immediately apparent. The spiral arms would appear as faintly luminous wisps against a background of almost absolute blackness. The gaps between individual stars would be visible as vast dark regions punctuated by isolated pinpoints of light. The overall impression would not be one of a dense, busy structure teeming with stellar activity. It would be one of overwhelming emptiness, interrupted by occasional widely scattered sources of light. The galaxy would look sparse. It would look lonely. It would look like what it is, a structure defined not by its matter but by the void between its matter. This perspective applies not just to the Milky Way but to every spiral galaxy in the observable universe. Andromeda, with its trillion or more stars, follows the same mathematics. The vast majority of its volume is interstellar space. The Triangulum Galaxy, the Whirlpool Galaxy, every grand design spiral and every modest dwarf irregular, all of them are predominantly void by volume. Stars are everywhere outnumbered by the void surrounding them. Interstellar medium is everywhere the dominant reality. Within the Milky Way itself, the distribution of interstellar space is not uniform. The spiral arms are denser than the interarm regions. The galactic center is more crowded than the outer disk. The midplane of the disk concentrates more gas and dust than the regions above and below it. But even in the densest parts of the galaxy, interstellar space dominates. The central molecular zone near the galactic core, one of the most active star-forming regions in the Milky Way, still contains far more volume of interstellar medium than volume of stellar material. The spiral arms, those bright highways of star formation visible in images of external galaxies, are enhancements in density relative to the interarm regions, not solid structures filled with matter. A spiral arm increases the local stellar density by perhaps a factor of 2 or 3 compared to the interarm baseline. This is significant for star formation rates and for the visual appearance of the galaxy, but it does not change the fundamental character of the environment. Even inside a spiral arm, most of the volume is interstellar space. The interarm regions themselves are particularly stark. Between the Milky Way's major spiral arms stretch vast tracts of galactic disk, where the stellar density drops and the interstellar medium becomes even more dominant. A hypothetical observer positioned in the middle of an interarm gap, far from any spiral arm, would see fewer stars in every direction. The nearest stellar neighbour might be 10 or 15 light-years away rather than 4 or 5. The isolation would be deeper, the void more conspicuous, the sense of emptiness more acute. Yet even this enhanced emptiness would differ from the standard interstellar environment only in degree, not in kind. The interarm medium is still gas at roughly the same range of densities, still threaded with magnetic fields, still saturated with cosmic rays. It is simply more of the same, extending over larger, uninterrupted distances. Above and below the galactic plane, the situation becomes even more extreme. The disk is where most of the galaxy's gas, dust, and young stars concentrate. Rise a few thousand light-years above or below the midplane, and you enter the lower reaches of the galactic halo. Here the interstellar medium thins further, gas densities drop, dust becomes scarce. The stellar population consists primarily of ancient stars in globular clusters and scattered halo-filled stars, relics of the galaxy's earliest epochs. The spaces between these stars can be enormous, tens or hundreds of light-years of near-perfect vacuum separating one dim red sun from the next. The halo is interstellar space at its most absolute, a realm where matter is so rare that the concept of an environment, in any terrestrial sense, barely applies. What all of this means is that the hostility of interstellar space is not a localized hazard. It is not a danger zone that a traveler might someday learn to circumvent by finding a safer route through the galaxy. There is no safer route. The interstellar medium is everywhere. It fills the spiral arms and the interarm gaps. It extends above and below the disk. It occupies the halo. It stretches between every pair of neighbouring stars in the galaxy, without exception. There is no corridor through the Milky Way that avoids the thin gas, the cosmic rays, the magnetic fields, the functional vacuum, and the light-year distances. These conditions are not features of a particular region. They are the defining characteristics of the galaxy itself. This realization carries implications that extend well beyond the practical question of whether humans could ever build a starship. It speaks to the fundamental nature of the Milky Way as a physical structure, and to the relationship between the galaxy's luminous components and the vast, dark spaces that separate them. The stars that we see, that we study, that we name and catalogue and build stories around, represent the galaxy's rarest features. They are remarkable precisely because they are anomalies, brief concentrations of matter and energy against a backdrop of near-nothingness that stretches for light years in every direction. A star is what happens when a tiny fraction of the interstellar medium collapses under its own gravity and ignites. It is a temporary local violation of the prevailing emptiness, a pocket of extreme density and temperature embedded within a medium that is, by any human standard, empty and cold. When the star exhausts its fuel and dies, its material returns to the interstellar medium, dispersing back into the thin gas from which it came. The star was a momentary exception. The interstellar medium is the permanent state. Planets, moons, asteroids, comets, and everything else that orbits a star exist within the star's gravitational and, in many cases, magnetic domain. They are islands within islands, structures sheltered by the very anomaly that created them. Earth exists because a pocket of interstellar gas collapsed into the Sun and its surrounding disk 4.5 billion years ago. Everything we know, everything we have ever experienced, every ecosystem, every civilization, every individual life has unfolded on a tiny rocky body orbiting within the magnetic bubble of one star, itself a brief luminous interruption in the galaxy-spanning darkness. Beyond that bubble lies the interstellar medium, and beyond the neighbouring star's bubble lies more interstellar medium, and beyond the next star, and the next, and the next. More of the same, extending outward in every direction for 100,000 light-years, encompassing hundreds of billions of stellar oases separated by an ocean that offers nothing to anyone or anything attempting to cross it. This is the architecture of isolation. It is not designed. It is not intentional. It is simply the consequence of how matter distributes itself under the influence of gravity and thermodynamics in a universe governed by the physical laws we observe. Gravity pulls matter together into stars. Nuclear fusion converts that matter into energy for a few billion years. Then the matter disperses. Between the episodes of stellar concentration, the default state prevails. Thin gas, weak fields, cosmic rays, void. The galaxy is structured, at its most fundamental level, as a collection of isolated systems. Each star and its attendant planets exist within a tiny sphere of relative warmth and density, surrounded on all sides by an environment that is hostile not through malice but through absence. The barriers between these systems are not walls or shields or active defences. They are simply distance, multiplied by emptiness, compounded by time. And these barriers are not occasional features of the galactic landscape. They are the landscape. The stars are the exceptions. For any civilization, including our own, this architecture imposes a profound constraint. We can observe the galaxy. We can study its structure, catalogue its stars, analyse the spectra of its interstellar gas, and map its magnetic fields to extraordinary precision. We can know the galaxy in exquisite scientific detail, but knowing it and crossing it are different things entirely. The knowledge travels at the speed of light. A probe or a ship travels at a fraction of that speed, if it travels at all, through a medium that provides no assistance and exacts a continuous toll in radiation exposure, energy depletion, and material degradation over timescales that humble human patience. And here is the point that elevates this from a human engineering problem to something far more fundamental. The interstellar medium does not care how advanced the civilization attempting to cross it happens to be. A species 1 million years older than humanity, with technologies so sophisticated they might appear indistinguishable from magic to our eyes, would still face the same 1 atom per cubic centimetre, the same galactic cosmic ray flux streaming from every direction, the same absence of matter, energy and shelter between one star and the next. Technology can build faster ships. It can build better shielding. It can extend the duration over which biological or mechanical systems can function in hostile conditions, but it cannot change the medium itself. The interstellar gas does not become denser for a more advanced traveler. The cosmic rays do not politely diminish for a civilization that has mastered fusion or antimatter propulsion. The distances do not shrink, because the species attempting to cross them has been spacefaring for 100,000 generations. The medium is fixed. It is a property of the galaxy, set by the physics of gas dynamics, magnetic field generation, cosmic ray propagation, and gravitational structure formation operating over billions of years. No technology alters those underlying conditions. A starship can be designed to endure the medium more effectively, to cross it more quickly, to shield its occupants more thoroughly. But the crossing itself remains a passage through a region stripped of every resource, and the length of that passage remains measured in light years regardless of what powers the vessel. The barrier is not technological. It is geographical, in the deepest sense of that word. It is the shape of the galaxy, the structure of the space between stars, the physical fact that most of the Milky Way is made of something that is functionally nothing. This is what separates the interstellar problem from every other challenge in the history of exploration. The Atlantic Ocean was vast, but it contained fish, currents, wind, and islands. The Antarctic was brutal, but it had ice that could be melted and seals that could be eaten. Even the vacuum of interplanetary space offers solar energy in abundance and destinations distributed at intervals reachable within years. Interstellar space offers none of these mercies. It is a medium that cannot be harvested, cannot be used, cannot be modified, and cannot be shortened. It can only be endured. And it must be endured for years, decades, or centuries depending on the distance and the speed, with the full galactic cosmic ray flux bearing down on whatever dares to attempt the crossing. The medium does not adjust itself for ambition. It simply persists. The nearest star is 4.24 light-years away. The next nearest handful are scattered within 10 light-years. The nearest 100 stars are distributed within roughly 20 light-years. Beyond that, the numbers grow and the distances stretch, but the character of the medium never changes. It is always the same thin gas, the same magnetic fields, the same cosmic rays, the same absence of anything useful. A journey of 4 light-years and a journey of 4,000 light-years differ in duration but not in character. The interstellar medium is scale invariant in its hostility. It does not become easier or harder at different distances. It is simply more of the same, extending without interruption for as far as the galaxy reaches. This is why the terrifying truth about interstellar space is not reducible to a single dramatic fact. It is not that the temperature is extreme, although it is. It is not that the radiation is dangerous, although it is. It is not that the distances are vast, although they are. The terrifying truth is that all of these conditions combine to create a barrier that is not made of anything. It is made of nothing. The absence of matter, the absence of energy, the absence of shelter. The absence of any feature that could make the crossing less than a total commitment of resources and time, on a scale that may exceed what any physical system, biological or mechanical, can sustain. Emptiness is the barrier. Not a wall of stone or a field of energy, but the simple, patient, universe-spanning fact that between one star and the next there is almost nothing, and that almost nothing extends for trillions upon trillions of miles without a single interruption. The medium does not resist you, it does not fight you, it does not need to. It simply offers you nothing, and it keeps offering you nothing for years and decades and centuries, until either you arrive at the next island of warmth or you do not. When we look up at the night sky and see the stars, we are seeing the exceptions. The rare, beautiful, temporary exceptions to a rule that governs 99.9999999% of the galaxy. The rule is emptiness. The rule is the interstellar medium, thin and cold and saturated with radiation, stretching without relief between every point of light we can see. Those points of light are separated from each other by distances that transform their proximity from an invitation into a taunt. The stars are close enough to see. They are close enough to study. They are close enough to dream about. They are not close enough to reach, not easily, not quickly. Perhaps not at all within the constraints of physics as we currently understand it. And this is not a temporary condition. It is not an engineering problem waiting for a clever solution. It is a structural feature of the universe at the galactic scale. The Milky Way was built this way. Gravity assembled its stars from a medium that was already thin, already sparse, already stretched across distances that light itself requires years to traverse. The galaxy did not become empty between its stars. It started empty. The stars are the anomalies that formed within the emptiness, and the emptiness remains, as it has remained for billions of years, as it will remain for billions more, the dominant, permanent, unyielding feature of the galactic environment. There is something both humbling and clarifying about this recognition. Humbling because it reveals the true scale of our isolation. Earth is not merely a small planet in a large universe. It is a tiny pocket of warmth orbiting within the magnetic bubble of one star, surrounded on all sides by a medium that would strip away every protection and every resource we depend on for survival. The nearest alternative pocket of warmth is over 4 light-years away, across a gap that current technology cannot meaningfully bridge within human timescales. We are, in the most literal physical sense, alone on our island, able to see other islands in the distance but unable to reach them, clarifying because it puts the galaxy's beauty into its proper context. The Milky Way is magnificent. Its spiral arms are sweeping and elegant. Its star-forming regions blaze with the light of newborn suns. Its ancient globular clusters carry the memory of the galaxy's earliest epochs. All of this is real, and all of it inspires the awe that drives astronomy as a science and as a human endeavour. But the beauty is concentrated in the exceptions. The spaces between the beautiful things are vast and barren and silent, and those spaces are what the galaxy mostly is. We live in a galaxy of islands. Each island burns with nuclear fire, surrounded by a small family of worlds, wrapped in a bubble of magnetic protection, carrying within it the possibility of chemistry, complexity, and perhaps even life. But the sea between these islands is not water. It is vacuum. It is radiation. It is magnetic silence. It is distance measured in light years and crossings measured in millennia. And that sea covers so much more of the galaxy than the islands do that to call the Milky Way a galaxy of stars is to mistake the decoration for the building. The Milky Way is a galaxy of emptiness. The stars are what make it beautiful. The emptiness is what makes it real. And somewhere tonight, 2 small spacecraft built by human hands drift through that emptiness, carrying golden records etched with the sounds of a world they will never return to, falling silently through a medium that does not know they are there, heading towards stars they will never reach, the only human-made objects to have crossed the boundary between our sun's domain and the vast, quiet, terrifying truth that lies beyond. They will not arrive anywhere. They will simply keep going, growing colder, growing quieter, growing darker, until the last trace of their plutonium decays and the last signal fades, and they become what everything in interstellar space eventually becomes. Silent, drifting, alone, not because the universe is cruel, but because the universe is large and most of it is made of the space between things, and that space, indifferent and immense and older than any star it separates, is the truest thing the galaxy contains.